Alright, Reactivity 3.3. I will be going through this entire subunit really quickly because it's fairly short. Okay, let's start. Some background knowledge you would have to know is ozone. Now this is the atomic structure of ozone. You would also learn that ozone has a 1.5 bond, like that. But this is only when there's a delocalized electron kind of going around in these two oxygens to not connect, to form bonds with the central oxygen. However, you only draw this when they ask if there's a delocalized electrons. Otherwise, you would keep these two forms. This form and this form, they're the exact same thing, but just flipped. But you get the point. Another thing you have to know is CFCs. CFC is a chloro carbon, hence the word CFCs, okay? They are formed from fridges, ACs, and etc. And essentially what CFCs do is that, I'll go into this later deeper, but then essentially what CFCs do is that they kind of break down ozone. So the Earth right here, right? This is the Earth, this is the Sun. Oh, that's not good. Sun. Okay. And the sun exerts UV rays onto the Earth. And what you guys may have heard in middle school, or you guys should know, is that there's kind of like an ozone layer protecting Earth from said UV rays, okay? And UV rays, what ozone does is that it protects us from UVC rays. What UVC rays are, well, what they can do is that they can cause skin cancer, which leads to even more, which then transfer to other organs. So your other organs also have cancer and you would die. So in simple terms, it kills you. And what ozone does is that it blocks this UVC rays. However, CFCs, what they do is that they would form radicals and then react with ozone and then form O2, thus destroying our ozone layer, mainly in this hole and this hole, because the Earth is actually spinning. So all the CFCs all go up, and they'll all go up to our bottom, thus it will break this ozone layer, and UVC rays can come in, causing us skin cancer. Okay, so here's some background knowledge. And next is radicals. Radicals are, I guess, the most important thing. You can't really do much for Reactivity 3.3 if you don't know radicals. But they're really simple. The definition is a molecule or atom with unpaired electrons, and usually denoted with a dot on the side. So for example, chlorine radical would look like this, okay? Or an OH radical, because we know OH is minus usually in ionic form, but an OH radical would be like this. It doesn't matter where you put your radical sign. It could be here too, left or right, because the IB, it doesn't penalize you for writing it on the wrong side, but you get the point. And what a radical is, some properties of radicals is that since it has one single electron, so it's not even paired, this electron would want to form another bond, a bond with another electron, let's say another Cr radical. Thus, a radical is highly reactive. Okay. And this is something for what you have to know now. And next we can talk about homolytic fissions. Homo, you guys can link it to the word homosexual, which means same gender, like same gender, right? So homo means same. Or in chemistry, identical. I can't spell. Identical. Lytic means breaking down. You should be familiar with this word if you do bio, but it's good to know in chemistry too. So homolytic fission essentially is the same thing and it's breaking down. And a classic example is Cl2. If we draw the Lewis structure of Cl2, it's Cl, like this. And what homolytic fission does is that UV ray comes in, acting as catalyst. If you guys don't know what catalyst is, a catalyst is something that is another reaction that provides an alternate path with lower activation energy, thus the reaction would happen faster. Just keep that in mind. But UV rays come in, acting as catalyst, and breaks this covalent bond between, forming Cl. And since we know it's a homolytic fission, it will break the exact same. So it will form two Cl radicals. Okay? So this is homolytic fission. And because there's already a bond in Cl2, get my little pointer. There's already a bond here, right? So to break this bond, this is where UV energy comes in. It requires energy to break this already stable bond into making two unstable molecules. And the reaction mechanism is basically what I just explained to you. It's that UV rays come in and it breaks the bond directly. And these radicals, this is why it's bad, because these come from chlorofluorocarbons. And these radicals break down. They essentially they're in gaseous state, and they go to the ozone layer, which as explained earlier, it goes to the top of the Earth, and top and bottom of Earth. And so what this does is that the chlorine radicals will react. Chlorine radical plus an ozone reacts a ClO radical plus O2. And what this does is that then you can see that the ozone already goes away, but there's still a lot more ozone, right? Which then the ClO radical, because it's still a radical, it will still react with whatever it can. It will react with the ozone to form chlorine radical and 2 oxygen. Okay, it reacts with the ozone because oxygen, it's pretty stable, but then ozone, you can kind of think of it as a resonance. It has delocalized electrons, so it also wants to react. So anyways, so this just kind of shows you that it will only create oxygen. Give my little pointer. Your chlorine radical will only react with ozone to form ClO and oxygen, which then ClO radicals also react with the ozone to form oxygen and Cl radical, and this goes all the way back here and forms it again. And just a fun fact, about 1 chlorine radical can consume about 100,000 ozones, I'm pretty sure, which already puts you in perspective of how it destroys our ozone layer. Okay, moving on. This is radical substitution reaction. So what I've just talked about here, homolytic fission, the reaction mechanism is initiation. So when 2 non-radicals start to form radicals, then this is initiation. And next step is propagation, which is this, which is, the definition is when a radical forms another radical. And lastly is termination. Let me get a new page. Termination, where 2 Cl radicals form Cl2. So two radicals form forms a stable molecule. And so let me write down 3 steps. We have initiation, stable forms radicals. Propagation, where radicals form radicals. And let's erase this. And lastly is termination, where radicals form stable molecules. Okay, so these are the reaction mechanisms of radical substitution reaction. So just something else to keep in mind is that this will always be, I'm pretty sure, give me a second. This, your initiation will always be exothermic, right? No, endothermic. Your initiation step will always be endothermic. Let's write this better. Endothermic. Because it requires energy to break the stable bond. Remember the Cl? Get my little pointer. It required this UV ray to break down and form two radicals, okay? Your next step is propagation. This could be both endo or exo. It depends on what the question gives you, depends on the enthalpy. But you can't really calculate enthalpy, so when the IB really asks you, they would give you information and you would know. And last is termination, which is exothermic. Because now two Cl radicals, this is just an example, they release out energy to form the Cl2. So that will be exothermic. And yeah, that's it for reactivity 3.3. Reactivity 3.3.